Hello, welcome to Enigma, a series of videos in which I'm going to try to explain the mathematics of the World War II Enigma cipher and the many attacks on it, or at least some of the many attacks on it. So in this introductory video, I'm just going to spend some time explaining from a mathematical point of view how the machine worked. So what you'll need to know for this series is a little bit about permutations. No more than would be covered in a first course in abstract algebra. And then later on, perhaps we will use some basic statistics and probability. I'll be concentrating on the mathematics of Enigma, not the history or the engineering, but I'll try and give some references from time to time if you want to follow that stuff up. Okay, so let's begin by going through the functional parts of the Enigma machine one by one, starting with the keyboard at the bottom left of the slide right here. So the keyboard has 26 keys labeled A to Z in the layout that I've shown you. There are no numbers, no symbols, no upper or lowercase, no spaces, just those 26 letters. And the machine works by encoding one letter at a time. So when you press a key on the keyboard, it makes a circuit and an electrical signal is sent through the machine, and I'll show you the path of the signal. So it first travels from the keyboard into what's called a plug board or stecker board, which is a mechanical device, or electromechanical device that swaps some pairs of letters and leaves others alone. So exactly which pairs it swapped was something that you as a machine user could configure. So next, after that, the signal passes through a sequence of rotors, each of which, again, permutes the letters of the alphabet in some way. So usually there were 3 rotors, although there were many different Enigma variations, some of which had 4 rotors. So here we've got our 3 rotors, which we're going to refer to as the right hand or fast rotor, which is the first one the signal passes through, then the middle or medium rotor, and then after that the left hand or slow rotor. I will explain why they're called fast, medium and slow later on. So next, after that, the signal reaches what is called the reflector. And what the reflector does is to swap all 26 letters in 13 pairs. So it's a fixed point free involution. And after it's done that, it sends the signal back through the machine parts in the opposite direction. So it'll pass through the left-hand rotor in the opposite direction, then the medium rotor, then through the fast rotor, and then through the plug board. And then finally, after it's gone through the plug board, it exits through the lamp board. So that's the machine's output. There is one lamp for each letter of the alphabet, and one of those letters lights up. That tells you the output letter corresponding to whatever input letter you typed in the machine. So we can think of each encoding part of the machine as performing a permutation of the letters of the alphabet. And I've named the permutations here. Right, so starting off with the plug board, this one will be called S. And the special property of S is that S is an involution. It's a product of some disjoint 2 cycles. So for example, so let's say this is an involution. So for example, it might be something like if you'd chosen to connect 3 pairs of letters on the plug board, it might swap A, X, E, W, and S, T, like this. All right, now the 3 rotor permutations are just some permutations of the alphabet. There's nothing special about those. We'll refer to these things as L for the fast rotor, M for the medium rotor, N for the slow rotor. And then finally, the reflector permutation, we'll call that R, and the reflector permutation does have another special property. So this one is a fixed point free involution. So FPF, short for fixed point free involution. That means it is a product of 13 disjoint 2 cycles. It would swap all 26 letters of the alphabet in pairs. You'll see an example of a real reflector permutation that was actually used in one slide's time. Okay, so now that we've named the permutations performed by the various parts of the Enigma machine, we can record the overall permutation implemented by the Enigma. So what would happen is, starting off, the signal passes through the plug board, which implements S, then through the rotors, so we get L, M, N, like this, then through the reflector. And remember, the reflector then sends the signal back through the rotors and the plug board in the opposite order. So since it's passing through the left-hand rotor backwards, the permutation it experiences is the inverse of N, and then the inverse of M, and then the inverse of L, and then finally it goes back through the plug board and experiences the inverse of S. Now S is an involution, so S inverse is just the same as S again, but this is what happens. So we'll keep it as S inverse because what we can see here, and what keeping it as S inverse makes clear, is that this is a conjugate of R. I love working in central London. I love it. I love it when I'm trying to record something and you get an ambulance going past at maximum volume. I love it. So this is a conjugate of R. Okay, a conjugate of R. So since R was a fixed point free involution, any conjugate of R will also be a fixed point free involution. Try that again, a fixed point free involution. Okay, so that means the Enigma machine has a couple of properties. So first of all, because the Enigma permutation is always fixed point free, the Enigma machine never sends a letter to itself. So for example, M can never be encrypted to M again. All right, now second property, because the overall permutation is fixed point free involution, if it sends A to X, then it would also have sent X to A. And another consequence of that is that to decrypt a ciphertext encoded by the Enigma, all you have to do is put the machine in the exact same configuration used for encryption, type in the ciphertext, out will come the plain text. Okay, so that's the structure of the three-rotor Enigma machine. Let's take a closer look at some of the permutations implemented by rotors and a reflector. So here is an example of a couple of real examples of rotor and reflector permutations. So at the top there is the permutation implemented by the rotor, conventionally called rotor number 1 in Roman numerals, when it's in a particular what's called neutral position, which I'll describe in a moment. So what this permutation does, it's recorded in 2-row notation here, so that means it would send the letter A to E, B to K, C to M, D to F, and so on. And then you have it also on the right here in disjoint cycle notation. So you can see it doesn't have any obvious special structure. Yeah, okay. So there is one thing to say about the rotor permutations, which is that you can see here that this one has a single fixed point. Right? The only letter it sends to itself is the letter S. And indeed, if you look at some of the examples of real rotor permutations, so the first link at the bottom, which I'll copy into the description, in fact the second link at the bottom as well, has got some descriptions of quite a few real rotors. And if you look at those, you find that most of them don't have fixed points. So there are 10 real rotor examples in the first link below, and only 3 of them have got fixed points. If you choose a permutation of the alphabet uniformly at random, there's about a 2/3 chance that it would have a fixed point. So if you take if you draw 10 permutations of the alphabet uniformly at random, there's a very low probability, about 3%, that only 3 of them are going to have fixed points. So there's some evidence there that they chose their rotor permutations to avoid fixed points, but I don't know of any special structure that they have other than they were, the machine designers were obviously reasonably keen to avoid fixed points. Okay, let's move on and look at the reflector permutation. This is the permutation performed by the reflector known as reflector A. It was one of the actual permutations used in the machine when it was in use before and during World War II. So these reflectors didn't rotate. They weren't like the rotors. They at least in the standard Enigma machine, they did not rotate. And I've given you the reflector here again in two-row form and in disjoint cycle rotation notation. So this permutation would send A to E, B to J, C to M, and so on. And here it is in its disjoint cycle form. You can see that it really is a product of 13 disjoint 2 cycles. So it's an A to E and E to A, B to J and J to B, and so on. Okay, next slide, please. Like I said, the point of rotors is that they rotate, right? Each of the 3 rotors in the machine, but not the reflector, at least in the standard Enigma, could rotate, and they would do that in steps of 1/26 of a turn. Okay, so let's take a closer look at what these rotors actually look like. It's going to be important in understanding what happens when they rotate, so the effect of rotor rotation on the permutations implemented by the rotors. So on the left just here, I've got a side-on view of a rotor. So if you looked at the machine from the front, then this is how the rotor would be facing you. And around the outside of the rotor, this part here is what is called the alphabet tire. Let's write this in. This part here is the alphabet. So this alphabet tire, as the name suggests, was labeled with the letters of the alphabet equally spaced in their usual sequence. Although some rotors instead had the numbers 0 to 25 instead of letters, so occasionally we will identify the numbers 0 to 25 with the letters A to Z. And the rotors were removable. You could open up the machine, take the rotors out, rearrange them, put them back into the machine. And when you did that, when you put the rotors into the machine, there is a little window, so I've drawn it on the diagram in the middle there, a little window through which one letter on the alphabet tire was visible. And that visible letter is called the window position of the rotor. So once the rotors were into the machine, you could actually move them using this part of the wheel here, this part of the rotor there, so that your chosen letter appeared in the window. Okay, so let's move on to this diagram in the middle here. This is a rotor which is in, well, it's in neutral position. There's another component to what neutral position means, which I'll come to in a moment. But in neutral position here is a rotor in the machine, and part of what that means is that there are some input contacts for the rotor, so outside the rotor. So here, A, B, C, D, E. Our input contacts are labeled with the letters A, B, C, D, E up to Z. And what that means if the rotor is in the fast position, so if it's the first rotor which the signal encounters, it means that if you press the letter A, and if that wasn't moved by the stecker board, then the signal from that A would connect to the contact, the input contact labeled A. Okay, so after this happens, when the neutral, the signal passes into the rotor. So when the rotor contacts are also conventionally labeled with the letters A to Z, and part of being in neutral position is that the rotor contact labeled A is lined up with the input contact whose label is A. Now, inside the rotor, we have wires connecting input contacts and connecting the input side of the rotor with the output side of the rotor, which determine the permutation that it performs. So, for example, let's take another color here. For example, letter A might be connected to E. Okay, this isn't a real rotor wiring, it's just an example. to make it easy for me to draw it. So A might be connected to E, B might be connected to G, C might be connected to A like this, and D might be connected to D. There's nothing wrong with having fixed points like this, and so on. So every contact on the inside the rotor on the input side will be connected to another on the output side, like that. So if we call the rotor permutation M, then in my example here, M of A was equal to what was it? To E. M of B was equal to G, and so on. Okay, so let's look at what happens when the rotor rotates. So the right hand, or the fast rotor, moves 1/26 of a turn each time a key is pressed. So to be precise, the rotation happens before the signal goes through the circuit, and it rotates towards the keyboard, so in such a way that the letter in the window advances one step forwards through the alphabet. So you can see here in my diagram, we started off with an A in the window, and after one step of rotation, there will be a B in the window. Okay, so that continues until we get to a Z in the window, and then it goes back to an A again, and so on. So once in every full rotation of the fast rotor, it causes the middle rotor to rotate by one step, and once in every full rotation of the middle rotor, it causes the slow rotor to rotate. So that's why these things have their names. The fast rotor rotates once every key press. The medium rotor rotates on average once every 26 key presses, and the slow rotor rotates on average once every 26 squared key presses. All right, but what happens to the permutation implemented by the rotor when it rotates? So let's copy the wiring that I showed before into this diagram on the right here. So A, well, we can't see any A anymore. It's disappeared outside our field of view, but we know that it was connected to G, so it's still connected to G. B was connected to E, like this. C was connected to A, so that's going to be a bit of wiring that disappears off the bottom. D was connected to D, and so on. So for example, if the signal coming in came in through the output A, let's draw this, let's choose a color here. If our signal came in like this, so this is our signal in green, then A would get connected to, the input A is now connected to B, so it's gone one up through the alphabet. Then it follows the track of B from the input side of the rotor to the output side. But now that it's rotated towards the output side of the rotor, labeled with E, is connected to the letter one before it in the alphabet. So it will come out at the D contact on the output side of the rotor. Okay, so after this rotor has rotated by one step, what's happened is that an input of A has gone to B, and then that has gone under M to E, and then that is connected to the D output contact. Okay, so to describe that algebraically, it's helpful to introduce the alphabet cycle here. So this permutation P, which I will call the alphabet cycle, is the permutation that just cycles the letters in their alphabet order, so A to B, B to C, and so on, Y to Z, and then Z back to A again. And this lets us describe the permutation after a rotation of one step in terms of the original neutral position permutation M. So after one step, the permutation which used to be M becomes what happens? Well, we had to shift one up through the alphabet. So the first thing we'll do is P. Then we do the permutation M, which was the permutation which the rotor was doing before it rotated. And then it does p to the -1 because we've got to shift 1 down through the alphabet. Okay, so in fact, after I steps, we can describe it the same way, only this time the permutation will be p to the -I m p to the I. Okay, so we know how the permutation implemented by a rotor now changes when it rotates through a certain number of steps. Okay, so the final thing we need to know about rotors is that every rotor has an adjustable, what's called ring setting or Ringstellung. For obvious reasons, a lot of the terminology used about the Enigma machine is in German. So Ringstellung is another word for the ring setting. And the effect of the ring setting is as follows. So the ring setting can be a number between 0 and 25. And the effect of changing the ring setting is that it allows you to rotate the rotor wiring while leaving the alphabet tire fixed. So that even though the window position is A, for example, if you've changed the ring setting, then you can cause the rotor to perform the permutation that it would if it were in some other window position but had a ring setting of 0. So the effect of changing the ring setting on the rotor permutation is just the same as the effect of rotating the rotor without moving the alphabet tire. So that means that if you just know if you know what rotor you've got in the machine and if you know its window setting, you can't tell what permutation it's doing because you need to know the ring setting as well. Okay, so that's something crucial because when you look up a rotor permutation in, for example, the links that I showed you on the last slide, which you can find in the video description, each rotor will just be described using one permutation. So we need to know what that permutation is. Well, that permutation is what permutation the rotor does when it's in what's called neutral position. So that's with a window setting of A and with a ring setting of 0. That's the meaning of the permutation that you see when you look up one of the rotors in those links that I showed you on that last slide. Okay, so let's try and just record exactly what the ring setting does. Our rotors have ring settings from 0 to 25. Like I said, changing the ring setting just has the effect of rotating the rotor without moving the alphabet tire. And the convention we'll use for describing ring settings is as follows. If you've got a ring setting of J, a number between 0 to 25, a window setting of I, again identifying the letters of the alphabet with the numbers from 0 to 25, and if the neutral position permutation was M, then the overall permutation would be, in our convention, P to the J minus I times M times P to the I minus J. Okay, if you're wondering why we're using the opposite direction for ring settings that we did than we're using for window settings, this is the convention which is used in Python Enigma simulator, which I particularly like and which I will link you to in the future. Okay, so that's how rotors rotate. That's the effect of rotation and of ring settings on the permutation implemented by the rotor. Let's go on now and look at what are called turnovers. So remember, we have 3 rotors in the machine, right? A fast rotor, a medium rotor, and a slow rotor. And those are in the right hand, the middle, and the left position as you look at the machine facing the keyboard. And the right hand, or the fast rotor, we know that rotates 1/26 of a full turn every time a key is pressed. But I'm now going to describe exactly how the other 2 rotors move. So what happens is that every rotor has a special window position called the turnover position. And when that particular turnover letter is in the window, if the rotor is in the fast position, then when that window position moves, it will cause the next rotor, the medium rotor, to rotate. And when that rotor is in the middle position and it is in its turnover position, then when it next rotates, it will cause the slow rotor to rotate by a single step. So here are the turnover positions for the 3 rotors known as 1, 2, and 3. Their turnover positions are Q, E, and V. And what that means is, for example, when rotor 1 is in the fast position, and when the window setting changes from Q to R, it causes the rotor to its left, the medium rotor, to advance by 1 step. Okay, so let's take an example of this. We're going to suppose that we've configured the machine with rotor 3 in the slow position, rotor 2 in the medium position, and rotor 1 in the fast position, and that the window positions initially are A, and P for the slow, medium, and fast rotors. So after 1 step, by step I mean after you've pressed the keys once, so after you've encrypted 1 letter, what happens is the fast rotor changes to a Q in the window position, and nothing happens to the other 2 rotors. We've still got an A in the window for the medium and slow rotors. Okay, but now the fast rotor is in its turnover position. So when we press the key again, the fast rotor will change the window, the letter in the window for the fast rotor will change from Q to R, and that will cause a turnover in the medium rotor. So the medium rotor will then advance by 1/26 of a turn, meaning that instead of an A, we now see a B in the rotor. On the other hand, changing from an A to B is not going to cause a turnover in the slow rotor because our medium rotor is 2, its turnover position is E. So we'll still have an A here. Okay, and then the next step, the next key press will cause the fast rotor to advance to S, but again, nothing will happen to the medium rotor and nothing will happen to the slow rotor. So they'll still be in position A, B. Okay, and so on. All right, now there are certain circumstances in which it can be worse than this, more complicated than this. What can happen is, in certain circumstances, there can be a double turnover of the middle rotor. So it can turn over twice in consecutive steps. If you want to see examples of how this can happen, check out the second YouTube video at the bottom of the screen there, which again I will paste into the description. Or you can, if you prefer to read about this, you can look at the link in the middle, which is to a paper about double stepping or double turnovers. It explains exactly when this can happen. The first YouTube video there is by Jared Owen. It's a really good 3D animation of how rotors rotate in the Enigma machine and how turnovers happen. So I really recommend this. If you want, for some reason, to understand the actual engineering of the machine itself, then take a look at that first video. That will explain it much better than I could. Okay, so we know now how the rotors rotate and how each rotor can cause the next rotor, if there is one, to rotate, and when that happens. Let's move on to our last slide here, which is about key exchange. So when you want to transmit encrypted messages, at least before the invention of public key cryptography, which came much later than the Enigma machine, you need the sender and receiver to have some kind of shared secret key or cryptographic key that they can use for encryption or decryption. And the most important property of your cryptographic system is it should be hard for an unauthorized third party who's listening in on your encrypted transmissions to recover what the key is. So in the case of Enigma, this shared secret or cryptographic key, secret key, is the machine state. And we've already described the machine state, which consisted of 4 components, right? You had the plug board connections. So the plug board connections were variable. You could choose them. You had some number of plugs, and you could use them to connect pairs of letters on the plug board. Okay, so that was the first configurable part of the machine. The second is, remember that the rotors in the Enigma machine were removable. You could open up the machine, take out the rotors, put new rotors in, put them in a different order. So the second part of the machine state was which rotors were in the machine and which order they were in the machine. So whether they were in the fast, medium, or slow positions. Okay, thirdly, as we've seen, Each rotor had a ring setting, and the effect of the ring setting was the same as rotating the rotor without actually moving the window position. And finally, we have the window positions themselves. So once you've put the rotors into the machine, you could rotate them to choose the window position. So in the context in which Enigma was actually used, senders and receivers agreed the secret key by using a key sheet, which was a piece of paper listing machine configurations to be used on specified dates or at specified times. And I've got an example of a real key sheet over here. You can see that this was a key sheet used by the German Air Force towards the end of World War II. Let's just talk through what's on the key sheet here in this column right here. What you've got is the dates. You've got what have you got? You have dates, so days of the month. So you've got 1 up to 31 there. They're in that order, so from 31 down to 1, because once you'd used a day, I think you were supposed to tear off or cut away that day's keys and then destroy them, so that even if the key sheet was found, at least it would be missing the information from the previous days. Okay, next after this, you've got the wheel order. So what this is saying, for example, in this top row, is that on the 31st of the month, the wheels you were supposed to put in the machine were wheel 1, wheel 5, and wheel 3 in that order. Okay, next, the next column specified the ring setting. So here, this, if you can't quite read that, it says Ringstellung, and it says that the wheel 1 should be put in ring setting 14, wheel 2 should be put in, wheel 5 should be put in ring setting 9, and wheel 3 should be in ring setting 14. Next part, you should ignore this next part. That's something which, that's a special adjustment which didn't exist in the simple version of the Enigma that we're looking at. So that's how you can tell that it's from late on in the war. The next part after that is the stecker board settings, or the plug board settings. So this is saying that you should take 10 plug wires, use them to connect S to Z, G to T, D to V, and so on. The last part, the last two columns, again, you should ignore them. They're not relevant to the machine settings. But this is how the secret key, the machine settings, will be specified using a key setting, using a key sheet very like this one. But there's one important problem. So one important problem is that this key sheet would, for logistical reasons, be shared by quite a large, in some cases, network of message senders and receivers. And that causes a problem, because if everyone just encrypted their messages by looking at the settings for the particular day, configuring their machine so it had those settings, and then typing in their messages, then every message sent by everyone on that network would use the exact same encipherment to encode their messages. And this is a bad weakness for a cryptographic system. When you have everybody using the same machine configuration for their messages, those messages are said to be in depth, and cryptographers hate this. They hate it because it's a serious cryptographic weakness. So no matter what your cipher is, it's always a weakness to have lots of messages in depth. So they had to avoid this, which means that the key sheets weren't the end of the story as to how people configured their machines before encrypting messages. So what in general would happen is that you'd use the key sheets to specify part or all of the machine state, but actually each individual message would be transmitted using a different, what was called message key, which would be based on the specifications in the key sheet, but chosen by the sender and hopefully unique to each individual message. So it would generally differ from the key sheet settings only in a small way. So for example, only by having different initial window positions. There were various different message protocols used for communicating this message key to the receiver, used at different times and by different networks. Some of them were very poor, others were more effective. We will go into the details when we look at some of the attacks on the Enigma in future videos. So for now, that's all. Hope you enjoyed the video. Post any questions you've got in the comments, and that's it.